He wasn't studying electricity, at least not in the way history says it existed. On his desk sat a stack of architectural drawings, brittle with age, pulled from the basement archives of a courthouse that had stood since the 1860s. The ink had faded, the signatures were barely legible, but one detail kept pulling his attention back, over and over again. The basement level was incomplete. Not damaged, not lost by accident, but simplified. Entire sections reduced to blank space, as if something had been intentionally removed before anyone else could see it. Next to the drawings was a piece of copper sheeting cut directly from inside one of those walls during renovation. It wasn't decorative. It wasn't structural. It was embedded deep between layers of stone and mortar, placed with precision, running continuously along the interior like a hidden circuit. No record of it existed in the official plans. No explanation accompanied its presence. For 30 years he followed patterns like this across dozens of buildings, train stations, hospitals, city halls, structures all officially built before electricity was supposed to exist as a usable system. And yet, inside them, he kept finding the same thing: conductive materials, arranged deliberately, basement levels that were more complex than necessary, metal pathways that mirrored the logic of modern electrical distribution, but without any documented power source. By the time he began writing his report in 1899, he wasn't asking whether something was wrong with the buildings. He was asking something far more dangerous. What if the buildings were working exactly as designed, and history was wrong? He wrote in the language of an engineer, not a theorist, documenting physical evidence, tracing pathways, mapping conductive systems that had no business existing inside structures labeled as pre-electrical. He wasn't speculating. He was describing. But the report was never published. He was told to stop quietly, without explanation that made it onto paper. Within a year he retired. Shortly after, references to his work began appearing only in fragments, a memorial note here, a missing survey there, each one repeating the same careful phrase, that his findings were left incomplete for reasons unrelated to their technical merit. And then, nothing. For over a century, the buildings remained. The systems remained, hidden in plain sight, sealed behind stone, buried beneath official explanations that no longer seemed to fit what was physically there. The question is not whether he found something. The question is why no one was allowed to finish what he started. The buildings themselves do not behave like historical artifacts, they behave like systems, and the deeper engineers have looked into them, the harder it becomes to reconcile what is physically present with what the official record claims should exist. Across cities in the northeastern United States, structures built between the mid-1850s and the turn of the 20th century share a pattern that is too consistent to dismiss as coincidence. Train stations, courthouses, hospitals, and exhibition halls, all constructed within this narrow window of time, exhibit a level of material precision and internal complexity that exceeds what their documented budgets and construction methods should have allowed. Stonework is tighter, metals are placed with intention, and beneath it all, hidden from public view, are layers of systems that do not match their stated purpose. The first anomaly is structural excess. These buildings were not simply built to stand, they were built to endure forces and conditions that were never officially described. Walls are thicker than required, foundations extend deeper than necessary, and basement levels, often classified as storage or mechanical space, are far more elaborate than their labels suggest. In many cases, these lower levels are constructed with greater care than the floors above them, as if their true function was never meant to be seen. The second anomaly is material placement. During renovations conducted over the past century, engineers have repeatedly uncovered continuous copper elements embedded within walls and floors. Not wires in the modern sense, but sheets and heavy-gauge pathways, positioned in direct contact with stone materials such as limestone and marble. These placements are not random. They follow consistent routes, forming networks that resemble distribution systems, yet they are absent from the original architectural drawings. That absence is not a minor oversight. 19th century drafting practices were meticulous, especially for large civic projects. Structural components, load-bearing elements, and material specifications were carefully recorded. And yet, in building after building, the areas where these conductive materials are found correspond precisely to the sections where documentation is incomplete, simplified, or entirely missing. This leads to the third anomaly, and perhaps the most difficult to ignore. The routing of these embedded systems follows the same logic as modern electrical infrastructure. From a central point, usually located in the basement or sub-level, pathways extend outward, distributing through walls and floors to upper sections of the building. It is a pattern of intentional design, not accidental inclusion. At first glance, the official explanation seems sufficient. Gas lighting, steam heating, and basic mechanical systems powered these structures. That is the accepted narrative. But when engineers began tracing these embedded elements, measuring their continuity, and examining their interaction with surrounding materials, that explanation started to weaken. Because gas lines do not require continuous copper sheeting embedded in stone, steam systems do not need conductive pathways routed through walls in symmetrical distribution patterns, and storage basements do not require what appear to be large-scale arrays of metal components arranged with precision relative to the building's thermal mass. Something else was being built into these structures, something that was never fully documented, and more importantly, something that does not fit comfortably within the technological framework assigned to that period. The question is not just what these systems are, it is why they were never meant to be seen. Because by the late 1890s, when electrical engineers were first brought in to retrofit these buildings for the emerging power grid, they encountered interiors that did not behave like blank slates waiting for wires. They encountered structures that already contained something organized, something functional, and something that did not belong to the story they had been told. And that is where the pattern begins to shift. When electrical engineers entered these buildings in the late 1890s, they did not arrive as historians. They arrived with a specific purpose: to install a wired system that would connect every structure to a centralized power grid. Their framework was simple: identify where wires should go, where fixtures should be placed, and how power could be distributed from an external source into the building. But what they found inside complicated that process in ways that were never fully explained. In multiple survey reports from that period, references begin to appear, not as conclusions but as quiet observations. Conductive pathways already present, unusual metal configurations embedded within load-bearing walls, basement systems that required careful navigation, not because they were fragile, but because their function was unclear. These were not the kind of notes engineers were trained to make without reason. And then, something even more unusual begins to happen. The reports stop. Projects that were initiated to systematically examine large civic buildings, surveys that were funded and staffed, simply vanish from the record before completion. In the engineering journals of the early 1900s, there are repeated mentions of investigations that were begun but never finalized, studies referenced in passing but never published in full. Individually, each case could be explained away. Collectively, they form a pattern that is much harder to ignore. This pattern aligns almost perfectly with a moment of intense financial consolidation in the American electrical industry. The year 1899 sits at the center of this shift. Just 3 years after the Niagara Falls power station began transmitting alternating current to Buffalo, proving that electricity could be distributed over long distances, and at the exact moment when companies like General Electric and Westinghouse were locked in competition to define the national standard. But behind that competition was something larger: control. The emerging power grid was not just a technological system, it was a business model. Electricity would not simply be generated, it would be measured, sold, and billed. Every building connected to the grid would become a point of consumption, every user a customer, every unit of energy a transaction. For that model to work, one condition had to be true. Power had to come from the outside. Any system that allowed buildings to generate or distribute energy internally, without the need for metering, without continuous billing, represented a direct threat to that model. Not a theoretical threat, but a financial one, measured in terms that would scale across entire cities, entire industries, and eventually entire economies. And this is where the story of Nikola Tesla intersects with the engineers who were quietly documenting what they found inside these structures. Tesla's work on wireless power transmission, particularly his Wardenpfeife project, was based on a principle that electricity did not have to be confined to wires. It could be transmitted through the Earth itself, through the atmosphere, distributed without direct connections, without meters. Initially funded by powerful financial interests, the project quickly lost support when its implications became clear. Because a system that cannot be metered, cannot be controlled in the same way. The withdrawal of funding was not subtle, it was decisive. Tesla's access to capital disappeared, his ability to continue large-scale experiments collapsed, and his work shifted from public demonstration to fragmented correspondence and theoretical writing. In those private letters, he made a claim that rarely appears in official summaries of his work. He suggested that what he was developing was not entirely new, he believed it was a rediscovery. At the same time, engineers working inside existing buildings were encountering physical systems that, while not identical to Tesla's designs, operated on principles that seemed to echo the same idea. Energy not delivered, but produced. Not centralized, but distributed. Not built, but inherent to the structure itself. This convergence between what was being discovered in old buildings and what was being proposed in new experiments created a tension that went beyond engineering. It became economic. Because if even part of this was true, if buildings constructed decades earlier already contained elements of a system that reduced or eliminated the need for external power, then the rapid expansion of the electrical grid was not simply progress. It was replacement. And replacement on that scale requires more than innovation. It requires silence around what came before. That silence becomes easier to understand when you look not at the technology, but at the incentives surrounding it. Because by the turn of the 20th century, the question was no longer how electricity could be generated, it was how it could be sold. The wired grid offered something no distributed system ever could: precise measurement. A meter at every location, a bill for every unit consumed, a structure where energy was no longer a property of a building, but a product delivered from outside. This transformed electricity from a phenomenon into a commodity, and commodities, unlike natural processes, can be controlled, priced, and scaled. Now consider the alternative. If large civic buildings constructed in the mid-19th century were already incorporating systems that could produce low-level electrical output through their own materials and structure, through thermal gradients, mechanical stress, and conductive pathways embedded within stone, then those buildings did not require continuous external supply in the same way. They may not have powered entire cities, but they could have reduced dependence, lowered demand, and most importantly, disrupted the assumption that power must always come from a centralized provider. This is where the physical mechanisms begin to matter. The thermoelectric effect, documented in the early 1820s, describes how a voltage is generated when two different conductive materials are joined and exposed to temperature differences. Large masonry buildings naturally create these gradients, between interior and exterior walls, between basement and roof, between sunlit surfaces and shaded sections. If conductive materials are embedded strategically, those differences can be harvested. The piezoelectric effect, formally described in the late 1880s, shows that certain crystalline materials generate electrical charge when subjected to mechanical pressure. Stone structures, constantly shifting under load, temperature expansion, and environmental stress, create exactly those conditions. Individually, these effects produce small outputs, but architecture is not individual, it is cumulative. When scaled across an entire structure, with continuous conductive pathways, capacitive materials, and centralized collection points, those small outputs can combine into something usable, something persistent, and something that does not require fuel. And this is precisely what engineers began to suspect when they encountered basement systems that resembled large-scale arrays, not random assemblies, but organized configurations of metal, stone, and spacing, positioned relative to the building's thermal mass. In some cases, these arrays were connected through continuous copper pathways extending upward through the structure, following the same distribution logic as modern electrical wiring. Yet none of this appeared in the original documentation. Architectural drawings from that period, where they exist, often lack detailed representation of basement and sub-level systems, not entirely missing but simplified, reduced, as if the most complex portions of the building were intentionally underrepresented. This is not how incomplete archives behave. Random loss produces random gaps. What appears here is selective absence, concentrated exactly where the most unusual features are found. Renovation teams in the modern era have confirmed this pattern. Walls opened during restoration reveal layers that were never meant to be seen. Copper sheets placed between masonry courses, metal elements embedded within mortar designed for consistent thermal conductivity, configurations that require planning, precision, and intent. These are not accidental inclusions, they are engineered features, which leads to a more difficult question. If the builders of these structures did not possess the theoretical framework to fully describe these phenomena, as conventional history suggests, then where did the design knowledge originate? This is where the narrative begins to extend beyond individual engineers and into institutional structures. Professional engineering societies at the time were not isolated academic bodies. They were closely tied to industrial interests, funded by the same companies that stood to benefit from the expansion of the electrical grid. Their publications, their leadership, and their standards were all influenced, directly or indirectly, by the economic priorities of that moment. In such an environment, suppression does not require overt censorship, it requires alignment. A report that challenges the emerging model does not need to be banned, it only needs to be delayed, questioned, redirected. Reviewers raise methodological concerns. Editors request revisions that are never quite sufficient. Authors are encouraged to focus on less controversial aspects of their findings. Over time, the work fades, not because it was disproven, but because it was never fully allowed to exist. The engineer who began writing his report in 1899 was operating within this system. His work, described later as comprehensive and technically sound, was not rejected outright. It was simply never completed, never finalized, and never published in a form that could be examined, replicated, or challenged. And as the wide grid expanded, as buildings were retrofitted, as new standards replaced old systems, whatever had once been embedded within those structures became irrelevant, not because it stopped working, but because it was no longer part of the model. And once something falls outside the model, it does not need to be destroyed, it only needs to be forgotten. And forgetting, in this case, did not happen all at once. It happened gradually, layered over time, until what remained was not a clear record, but a series of gaps that are only visible when you know where to look. One of the most revealing patterns appears in the architectural archives themselves. For buildings constructed before the mid-19th century, documentation is often remarkably complete. Detailed drawings, material specifications, structural plans preserved with care. For buildings constructed after the early 20th century, the same level of detail returns, sometimes even more precise as drafting standards improved. But in the narrow window between those periods, roughly from the 1860s to the turn of the century, something changes. Basement drawings are missing. Sub-level plans are simplified. Sections that should contain the most technical detail are reduced to outlines, placeholders where complexity should exist. This is not consistent with accidental loss. It is consistent with selective omission, the kind that occurs when certain information is not meant to be preserved in the same way as the rest. Researchers who have examined collections maintained by organizations like the American Institute of Architects have noted this pattern repeatedly. Entire sets of drawings remain intact, except for the portions that would correspond to the areas where modern renovation has uncovered the most unusual embedded systems. It is as if the visible structure of the building was documented for public record, while the internal mechanisms were treated differently, either excluded, altered, or recorded in forms that did not survive. At the same time, within the professional literature of the early 20th century, there are traces of investigations that seem to approach these questions, only to stop short. References to surveys of existing civic buildings, notes about unusual internal configurations, brief mentions of conductive systems that did not align with standard models, and then nothing. No conclusions, no follow-up, no comprehensive publications that bring these observations together. Even more telling is the pattern of professional activity surrounding these investigations. Engineers who were actively involved in examining pre-grid structures in the late 1890s begin to disappear from the record shortly after. Not dramatically, not in ways that draw attention, but quietly. Retirements occur earlier than expected. Research trajectories shift. Papers that might have expanded on initial findings are never written. Individually, none of these details prove anything. But together, they form a convergence that is difficult to ignore, because this period of fading inquiry aligns almost perfectly with the period of maximum financial investment in the electrical grid, as infrastructure expanded, as urban centers were wired, as the utility model took hold. The incentive to maintain a consistent narrative about how power was generated and delivered became stronger, not weaker. A narrative in which electricity begins with centralized generation and flows outward through controlled channels is not just a technical description. It is the foundation of an entire economic system, and systems like that do not accommodate contradictions easily. If evidence existed, even in fragmented form, suggesting that an alternative approach had once been implemented, an approach embedded within the buildings themselves, independent of external supply, then that evidence would not need to be aggressively erased. It would only need to be excluded from the framework that defines what is considered relevant, teachable, or worth preserving. Over time, exclusion becomes absence, and absence becomes assumption. This is how a generation of engineers could work inside buildings that contained features they did not fully understand, document those features in limited ways, and then move on as the industry standardized around a different model. It is how architectural records could remain intact in most respects while omitting the very systems that might challenge the accepted narrative. And it is how a technical report, written by someone with direct access to these anomalies, could simply fail to enter the historical record in any meaningful way. The buildings, however, did not change. They were retrofitted, rewired, adapted to fit the new system, but the underlying structures remained, layers of material and design choices that continue to reflect an intention that has never been fully explained. In some cases, those original systems may no longer function as they once did, altered by renovation, disconnected from whatever conditions made them effective, but their presence is still there, waiting to be recognized not as isolated curiosities, but as parts of a larger pattern. A pattern that suggests the story of how buildings were powered, and more importantly, why that story changed, may not be as complete as it appears. And when that pattern is extended beyond individual buildings, it begins to reshape something much larger, not just how structures functioned, but how entire systems of energy were defined, replaced, and ultimately controlled. Because the transition that took place at the turn of the 20th century was not simply technical, it was economic at a scale that is difficult to fully grasp. The wired electrical grid did more than deliver power. It created a continuous relationship between provider and consumer, one that did not end after construction, but extended indefinitely, measured in usage, billed in cycles, and enforced through infrastructure that only a centralized authority could maintain. Under that model, a building is incomplete on its own. It requires connection. It requires supply. It requires participation in a system that exists outside of itself. But if even a portion of the revisionist claim holds, if buildings constructed decades earlier incorporated embedded systems capable of generating low-level electrical and thermal output through their own materials and design, then those structures operated under a fundamentally different assumption. Power was not something delivered to them. It was something inherent within them, something produced continuously as a byproduct of their interaction with the environment. That difference is not minor. It is the difference between ownership and dependency. In a distributed model, the cost of power is largely contained within the construction of the building itself. Once built, the structure provides its own baseline energy, not in unlimited quantities, but in a steady, maintenance-free way that reduces the need for external input. In a centralized model, the cost never ends. Power becomes a service, and like all services, it must be paid for repeatedly, indefinitely. Now extend that across an entire nation, across decades, across generations. The financial implications are staggering. Modern utility systems generate hundreds of billions of dollars in annual revenue, each payment tied to the assumption that energy must always be supplied from outside, always measured, always billed. If an alternative approach once existed, one that reduced or eliminated that dependency at the building level, then its disappearance would not just be a historical curiosity, it would be a turning point. And turning points of that magnitude rarely occur without resistance, or without consequence. The engineer who attempted to document these systems in 1899 was not writing economic theory. He was describing physical reality as he encountered it, copper embedded where it should not be, basement arrays that serve no documented purpose, conductive pathways that mirrored electrical logic without any visible source. But the implications of what he was documenting extended far beyond the technical, because a technical document, if published, if validated, if expanded upon, could lead to replication, and replication could lead to disruption, not necessarily of the entire system, but enough to introduce doubt, enough to challenge the assumption that the wired grid was the only viable path forward. In an industry built on scale, investment, and long-term infrastructure, even a small disruption can have cascading effects. So the simplest solution is not to disprove the findings. It is to prevent them from spreading, not through overt suppression, not through visible censorship, but through the quieter mechanisms that operate within professional communities. Delays, redirections, silence, a report that is never finalized, a survey that is never completed, a line of inquiry that gradually loses support until it disappears from active discussion. And once it disappears, it does not leave a clear absence. It leaves a gap that future generations no longer recognize as missing. This is why the story does not end with a single engineer, or a single report, or even a single period in time. It extends into the present, into the way buildings are understood, the way energy systems are taught, and the assumptions that are rarely questioned because they appear so complete. But completeness can be constructed. And when you begin to look at the physical evidence, at the materials, the layouts, the inconsistencies between what is documented and what is found, it becomes harder to ignore the possibility that something else once existed alongside the system we now take for granted. Something quieter, something embedded, something that did not require permission to function, and something that may have been left behind, not because it failed, but because it could not be controlled. By the time the 20th century fully took hold, the transition was complete, not just in infrastructure, but in perception. The wired grid was no longer seen as a choice, it was seen as the origin. Electricity in the public mind began at the power plant and ended at the socket. Anything that did not fit within that path was no longer considered part of the system at all. And this is where the final layer of the pattern becomes visible, not in what was added, but in what quietly remained. Because the buildings from the mid-19th century were never demolished on a large scale. They were preserved, repurposed, renovated, adapted to fit the new model, but their core structures, the walls, the foundations, the embedded materials, stayed intact. Layer after layer of modernization was applied over them. Wiring installed, fixtures replaced, systems updated. Yet beneath all of that, the original configurations were left in place, largely untouched, unless renovation forced them into view. And when those moments occurred, when walls were opened, when floors were removed, when basements were excavated, the same details continued to appear. copper where no copper should be, metal pathways that followed no documented plan, structural layers that served no visible purpose within the accepted framework. Not everywhere, not in every building, but often enough to raise a question that has never been fully answered. If these features are meaningless, why are they so consistent? And if they are meaningful, why were they never recorded? The official explanation does not engage with these questions directly. It does not deny the existence of unusual features, but it categorizes them as anomalies, construction artifacts, or remnants of outdated systems that no longer apply. That approach works as long as each case is viewed in isolation, but when viewed together, across cities, across decades, across building types, the pattern begins to resist that kind of dismissal, because repetition implies intention, and intention implies design, which brings the story back to the engineer whose work was never completed. He was not the only one who saw these things, but he may have been among the last to attempt a comprehensive explanation before the window for that kind of inquiry quietly closed. His report, described later as technically sound yet never finalized, represents more than a missing document. It represents a moment when the question was still open, when the evidence had not yet been fully absorbed into a different narrative. After that moment, the direction was set. Education aligned with the grid model. Engineering standards evolved around centralized distribution. Alternative interpretations, whether correct or not, lost the institutional support required to develop into recognized fields of study. Over time, the absence of discussion became indistinguishable from absence of evidence. And yet, the evidence did not disappear. It remained embedded in stone, in metal, in the physical reality of structures that continue to stand long after the context of their construction has been simplified into a version that fits more neatly within modern understanding. So the question is no longer whether something unusual exists within these buildings. The question is whether anyone is still willing to examine it without assuming the answer in advance. Because if the systems the engineer was documenting were real, if they operated on principles that were understood, applied, and then set aside, then the history of how buildings were powered is not just incomplete. It has been rewritten. And if it has been rewritten, then what else, built into the foundations of everyday life, is not what it seems to be.